Hi learners, welcome to my channel. Today, let's discuss in our podcast class on electric chargers and electric fields. Sit back, relax, listen and learn. Inside each atom, there is a nucleus with positively charged protons and chargeless neutrons and negatively charged electrons orbiting the nucleus. This is the basic atomic structure. Usually, there are as many electrons as there are protons, and atoms themselves are neutral. But you see, if an electron is removed from the atom becomes positively charged because electrons are negatively charged. When you remove one negatively charged electrons, the atom as a whole becomes positively charged. Then it is called a positive ion. If an electron is added in excess to an atom, then the atom is negatively charged and it is called negative ion. Okay, now you see, when you rub a plastic comb on your dry hair, the comb obtains power to attract small pieces of paper. Isn't it not? You have learned this and done this experiment in your 6th standard itself, isn't it? So when you rub the comb vigorously, electrons from your hair leave and accumulate on the edge of the comb. Now your hair is positively charged as it has lost electrons, and the comb is negatively charged as it has gained electrons. What is the value of these charges? Yes, electric charge is measured in coulomb and the symbol for the same is capital C. The charge of an electron is numerically a very tiny value. The charge of an electron is the fundamental unit with a charge equal to 1.6 into 10 power minus 19 coulomb. Okay, this indicates that any charge has to be an integral multiple of this fundamental unit of electric charge, that is Q is equal to N into E, where N is a whole number. Practically, we have microcoulomb, nanocoulomb and picocoulomb. What are their values? 1 microcoulomb is 10 power minus 6 coulomb. 1 nanocoulomb is equal to 10 power minus 9 coulomb and 1 picocoulomb is equal to 10 power minus 12 coulomb. Know this, electric charge is additive in nature. The total electric charge of a system is the algebraic sum of all the charges located in the system. For example, let us say that a system has two charges, that is plus 5 coulomb and minus 2 coulomb. Then the total or net charge on the system is plus 3 coulomb. These electrostatic forces between 2 point charges obey Newton's third law. Yes, what is Newton's third law? For every action, there is an equal and opposite reaction. Yes, the force on one charge is the action and the other charge is reaction and vice versa. Now moving on to electric force. What is electric force? Among all electric charges, there are two types of electric forces. Okay, so one is attractive and the other is repulsive. We already know that like charges repel and unlike charges attract. Basic physics, isn't it? You might have learned in 5th standard or 4th standard. Yes, what is electric force? The force existing between the charges is called electric force. These forces can be experienced even when the charges are not in contact. Next, moving on to electric field. The region in which a charge experiences electric force forms the electric field around the charge. Often, this electric field is represented by lines and arrowheads indicating the direction of electric field. The direction of the electric field is the direction of the force that would act on a small positive charge. Therefore, the lines representing the electric field are called electric lines of force. These electric field lines have certain properties. What are they? Electric lines of force start from positive charges and end at negative charges. In the case of a single charge, they may start or end at infinity. Okay? Tangent to any point on electric lines of force shows the direction of electric field at that point. You see, two field lines can never intersect each other, because if they intersect, then two tangents drawn at that point will represent two directions of field at that point, which is not possible. In a charge-free region, electric field lines can be taken to be continuous curve without any breaks. Electric field lines do not form closed loops because of conservative nature of electric field. Electric lines of force are perpendicular to the surface of a charged container. This one is so interesting, you see. Electric lines of force contract lengthwise to represent attraction between two unlike charges. And what about repulsion? Yes, electric lines of force exert sideways pressure to represent repulsion between two like charges. These electric lines of force do not pass through a conductor. Hence, the interior of the conductor is free from the influence of electric fields. That's why we say you are safe when you are inside a car during thunderstorm. In conclusion, electric field at a point is a measure of force acting on a unit positive charge placed at that point. A positive charge will experience a force in the direction of electric field, and negative charge will experience in the opposite direction of electric field. That's all for today's class, learners. Happy learning. If you're new to the channel, please do subscribe, share with your friends, and give a like to this video. Hope you have enjoyed this podcast class. Stay tuned with me. Bye bye. I'm Judy.